Hello, I'm Dr. Ducey. I'm with Missouri Western State University, and I know it's been a little bit since we posted. It was a busy semester, so I'm really excited to be able to bring you kind of a fun demonstration today and an example, or a series of examples, in fact, of relative densities. Now, clearly I like to do demonstrations that involve gases, and I'm going to do that again today. And I've got a variety of gases here for us to look at. So on my left over here, you might see the 3 tanks of gases that I've got. So I've got a tank full of helium, some carbon dioxide, and then I also have a tank of dry nitrogen. And then here I have some really fun stuff in front of me. This is a lecture bottle of sulfur hexafluoride. So this is an extremely dense gas. And it's an inert gas that we use in semiconductor industry. So I'm going to show you some of the properties of this really dense gas. So I think where we'll start is with the densities of gases, and I have some information up here on the board today that describes the relationship between the density of a gas and its molar mass. So in general, the density of a gas is directly proportional to the molar mass through this equation right here. And I've also made some measurements today for my environment here in the lecture hall. And I can tell you it's 23 degrees Celsius in here today, and the pressure is 739 millimeters of mercury. So I've gone ahead and converted those over to the Kelvin scale and atmospheres and did some calculations for the densities of the gases that I'm going to show you today. So the density of helium under these conditions today is about 0.16 grams per cubic centimeter. The density of nitrogen is pretty close to the density of air, since air is about 80% nitrogen, so that's 1.12 grams per cubic centimeter. And then we're going to look at carbon dioxide, which we've seen in some previous demonstrations, so we know it's denser than air, and that's 1.76 grams per cubic centimeter. And then we make this giant leap down here to sulfur hexafluoride at almost 6 grams per cubic centimeter. So this is going to give it some really interesting properties. Now, at the end of this video, I'll do some of the calculations. So if you're interested in how to calculate the density based upon the laboratory measurements, I'll show you that at the end. If you just want to watch for the fun science, then you can skip that at the end. So let's start with some densities of gases. So I'm going to put some helium into my, and let's make sure that everything is shut off. I'm going to put some helium into my balloon here, and then we're going to tie our balloon off, and we're going to look at those densities. So let me go ahead and get my balloon filled up with some helium. Okay, and so of course if I tie my balloon off and I set it here on the counter, of course, it rises because the density of helium is less than the density of air, and so that's why my balloon has gone all the way up there to the ceiling. So I'll have to get a stepladder at the end of this and pull it down. So there's one example of the relative densities of helium compared to air. Now we've seen the densities of carbon dioxide before with some of the demonstrations I did, but I'm going to get some carbon dioxide in a balloon here for us because we're going to use it in just a little bit, and I'm also going to get some dry nitrogen. So let me go ahead and get my, my carbon dioxide filled up. Now with my carbon dioxide, of course if I set it on the counter, it is not going to go anywhere because its density is much greater than that of air. In fact, it's almost has weight to the balloon. In fact, I could put this on a balance and determine the mass of carbon dioxide that is in that balloon right now. Let me go ahead and get some nitrogen as well. So let's get that one filled up for us. Okay. Now I'm using nitrogen because it is very similar to air, but I'm using the nitrogen from the tank because it's nice and dry, so I don't have to be concerned with the contribution of atmospheric humidity to the density of the gas as we do our demonstration. So here's my nitrogen. Of course it's going to drop because it's very similar to air, so we would expect that because the balloon has some mass as well. And so we can see the difference in mass between these two balloons, right? So my carbon dioxide balloon weighs a lot more. Okay, so now I'm going to get that balloon full of sulfur hexafluoride. Let's take a look at that one. I'm going to do purple for that. And let's see what that kind of looks like. So here we go. So get some sulfur hexafluoride in there. It's about the same size, right? Pretty close. Okay, and I'll tie that off. And we're going to set it on the counter. There we go. I'll tell you, this balloon, it's heavy. It's weird to feel it, that a balloon would have so much mass associated with it. But you can see it drops like a brick. Whoop, I have to go retrieve my balloon now. So this thing has quite a lot of mass because of the density of that sulfur hexafluoride. So sulfur hexafluoride, my carbon dioxide, my carbon dioxide, there we go, and then my dry nitrogen. Now what I want to do is I'm going to demonstrate the density of that sulfur hexafluoride by placing some sulfur hexafluoride here into this container, and we're going to see it fill that container. So in order to do that, I'm going to take this nitrogen balloon, I'm going to put it down there in the bottom of my container. Now again, because it's more dense than air, it's going to displace the air out of my container, and we should see that nitrogen balloon rise because the difference in density between the two. So let me go ahead, I'm going to start to feed some sulfur hexafluoride into it. And here comes my balloon. It's starting to rise. And we're going to try and fill it up as much as we can. So basically I'm going to let that nitrogen balloon spill out of there, because that's the point where I know it has completely filled my container. Well, that's pretty close. All right, so I'm going to go ahead and stop there. So now you can see the density difference between that sulfur hexafluoride and my nitrogen. I wonder if I could put the carbon dioxide balloon on there as well. So let's put our carbon dioxide balloon on there and see what happens. And even carbon dioxide, which we know is more dense than air, floats on that sulfur hexafluoride because of the huge density difference between the two. Okay, so there's some fun things associated with the density of the gases. Now, one of the other things that's really kind of fun related to gases is that the speed of a gas, the rate at which the particles move, is also related to its molar mass. And in this particular case, it's inversely proportional to the molar mass. What that means in simple terms is the bigger it is, the slower it moves. Now right now I'm breathing out and in a whole bunch of, breathing in nitrogen and oxygen, and I'm breathing out nitrogen and oxygen and a little bit of carbon dioxide as well that I'm expelling. And so the sound of my voice is really related to the speed of the gas particles that I'm breathing out as they cross my vocal cords. So this is why if we take some helium, so let me get a little bit of helium here, right? And we do, of course, that fun thing that we do with helium, where we breathe it in and then talk. So I'll breathe in my helium here, and I'll talk, and it makes my voice very high. And that's because the speed of the helium atoms were moving very fast. In fact, they're moving almost twice as fast as the particles of gas in air move. So the sound of your voice gets much higher. Now, you might wonder what happens if we do the same thing with sulfur hexafluoride since it's so big, okay? So what I'm going to do is I'm going to try and get a big breath of sulfur hexafluoride. Here, let's put a little bit more in here, okay? And we'll try and get a big breath of it. We're going to see what happens. Now, if the same thing occurs that we saw with the helium, then my voice should get very, very deep, right? Okay, so let's get a big breath of the sulfur hexafluoride, and my voice should get very deep. So now you can hear how low my voice got. Let's try one more time. So my voice gets very deep as I expel the sulfur hexafluoride because those particles are moving much slower. So, got to get that sulfur hexafluoride out because I don't want it to sit in the bottom of my lungs because I need the oxygen, of course, to get in there. So there you go. There's a quick demonstration of the relationship between the molar mass of a gas, its density, and the speed at which those gas particles move. Now, a note before I finish, and again, I'll do these calculations that I did for you in just a little bit, so if you hang on, you'll see those calculations pop up in a short addition to the video. Be careful doing these kinds of things, okay? So, because your body needs oxygen, so I only breathe a little bit of the gas so that I could demonstrate for you, but I wouldn't want to breathe a lot of it because that would make me oxygen deficient, so we don't want to do that. Now, one of the other things is I didn't breathe carbon dioxide, and that's on purpose because breathing in carbon dioxide, it can dissolve into your blood, and it can change your blood pH if you're not careful. So you definitely don't want to do this demonstration using carbon dioxide. Sulfur hexafluoride is inert, helium is inert, and so they were two really simple things for me to demonstrate this for you. All right, that's it for today. Again, hang on if you want to see the calculations and how I did those. Otherwise, have a great day, and we'll be doing some more videos soon, so stay tuned to our YouTube channel. Okay, as promised, here is a quick example of how to calculate the density of a gas based upon laboratory conditions. And so, as I showed earlier in the video, the density of a gas is equal to its pressure times its molar mass divided by the universal gas constant and the temperature. It's important to note as you go through these calculations that the pressure is in units of atmospheres and the temperature is in units of Kelvin. So I told you our laboratory conditions were 23 degrees Celsius and a pressure of 739 millimeters of mercury. I got that off our barometer. And so I'm going to go ahead and do those conversions so that they're in the appropriate units. So I'm going to add 273 to my temperature to convert over onto the Kelvin scale, the absolute temperature scale. And then I divide by 760 millimeters of mercury because 1 atmosphere is equivalent to 760 millimeters of mercury. And that gives me a pressure of 0.972 atmospheres. I'm just going to do two calculations for you. I'll do the calculation for the helium gas. So helium has a molar mass of about 4 grams per mole. And so if we plug in all of these values into the equation that you see here above, where our density is going to be 0.160 grams per mole. So it's a very low density, and of course we saw our helium balloon fly all the way up to the ceiling. The density of the sulfur hexafluoride is a lot more because the density, or the molar mass rather, of sulfur hexafluoride is 146 grams per mole. It's a pretty massive molecule. And so if we plug in our values based on that 146 grams per mole for sulfur hexafluoride, we come up with a density of 5.84 grams per mole.